So let's talk about numeric attributes. So as I said, they can be integers, binary, real numbers, really anything. As far as dealing with they're real numbers, so you can use any method that involves adding those numbers, multiplying those numbers, doing anything with them. Sometimes you treat integers specially. So if you have an attribute that is integer valued, sometimes you don't do things with it that you would do with real numbers. But most of the time, the difference is ignored. Now, one important thing with numeric attributes is usually you need to normalize their values. So the data that comes in, typically you try to bring it to the same range. Why do you do it? It's because the raw data, the raw numeric data, you have no control over the scale on which it happens. So if you have one attribute that is measured in billions and another attribute that is measured in single digits, if you don't normalize them and put the data straight into a learning algorithm, lots of learning algorithms will get confused by that. So for example, all of the linear methods cannot handle that. All of the projection methods will do poorly on that. So the typical thing to do is you bring the data basically to the same scale, so that all units are roughly comparable to each other across all the numeric attributes. And the most common way to do it is by taking the mean value of the attribute, subtracting it from every value, and then dividing by the standard deviation. So then every attribute value is centered around 0, and it has a variance of 1. So they're all sort of on the same scale, all comparable to each other. Sometimes you do something different, so sometimes you project them to 0, 1 range, but most of the time subtract the mean and standard deviation works quite well. This makes sense. The 0, 1 only makes sense if there are definite max and min values that you don't expect to ever exceed in either direction. Numeric attributes are sensitive to outliers. So what are outliers? Outliers for a single attribute are basically numbers that are unusually large or unusually small. So let me give you an example. So suppose I have an attribute called height, and in my data I have individuals with the following heights. Right? So, and if you plot them, they might look something like that. Right? So these are those individuals, and then there's that guy. Right? So now you look at that data, and what's your immediate reaction? It's a typo. Nice. Right. So this guy probably has 182 centimeters height, and somebody just accidentally typed a 0 at the end. But this happens in real data. Right? It happens a lot more often than you would expect. Now, the effect of having that 0 is very, very dramatic. Basically, all of the real observations are shoved to one corner, and this guy is in another corner, and there's nothing in the middle. So that will royally screw up all kinds of learning algorithms. Now, would normalization take care of that? No, that's right. Because if you do the mean of that is going to be, what is it, 9 meters. Right? So you're going to subtract 9 meters from everyone's height. So that's not going to work. And then the variance is going to be huge. And the max-min normalization won't work either. So outliers, extreme values, cannot be taken care of automatically. It's actually a really hard problem to detect them and to deal with them. And you have to do that before you apply any kind of normalization, because normalization will just get confused by that. You will have, as the result of the normalization, the mean is going to be 0, and the variance is going to be 1. So it'll do what it says on the tin, but the result is going to be totally nonsensical. So you can't just count on the normalization to save you. You actually have to handle those in some way.